Okay, welcome to Lecture 18 of Submodular Functions Optimization and Applications to Machine Learning. Today is June 2nd, and it's not the penultimate lecture of this class, but it's soon to be the penultimate lecture of this class. Today we're going to be talking about some very important things relating to your final project. So those of you who are here you may consider yourself very lucky because this will be useful for you in a week and a half's time. In particular, we're going to be going over some of the details of this paper here, which I think that everybody at this point should have gotten a copy of and started reading. Can you raise your hand if you've done that? And then, of course, Fujishige and Isotani, this paper. And then I hope that today's lecture will offer some additional assistance to you in getting a sense of what this algorithm is all about. There's the usual thing. So basically we're down here. We're in lecture 18. The minimum norm point algorithm detailed. But first what we're going to do is we're going to finish up a couple of additional examples of the Lovász extension because there are some relevancies there. So let's just get right to it and do some review. So last time we saw that the Lovász extension is the same as the Choquet integral that was defined in the early 1950s. And we also saw that there are a variety of different ways of defining the Lovász extension. We're using the notation f tilde of the Lovász extension for submodular function f. And there are these different ways. We can define it this way, or this way, or this way, or as these integrals, these two different integrals. And there's an additional, if we combine the function f together, we can have just one integral. And that basically makes it easy to see a number of different properties of the Lovász extension. For example, like the fact that that you can construct the Lovász extension of the sum of two submodular functions, or a multiplication times the submodular function in this way, or a couple of different definitions for w being non-negative. This is one that's useful, that it's sort of linearly related to directions along the 1e axis, if that makes any sense. So alpha times 1e can be just alpha times f of whatever the ground set is. There's the positive homogeneity, which is true for alpha greater than 0. For alpha less than 0, it's not true. This property we saw, that it's tight for all points on the vertex. We have symmetry, and then essentially a partitioning property. These are all properties that are useful. One in particular that's very important is that you can get the minimum of the submodular function by minimizing the Lovász extension, which means that you can do convex minimization procedures on the Lovász extension and get a vector, a continuous vector that when, as we saw last time, can be rounded in a particularly easy way, you can get essentially a set of solutions of the submodular function minimization problem. Now, of course, it's not, you need to be able to evaluate the Lovász extension, and you can, of course, do that in general because of the fact that you can get point queries from it using Edmonds' greedy algorithm. So Edmonds' greedy algorithm is sort of core. It's sort of essential for many different properties of submodular functions. And as in this class we've sort of motivated, we've even said that when you start off with a matroid, remember matroids and greedy are sort of one-on-one, or one-to-one, right? They're identical to each other. And polymatroids and greedy are also identical to each other in the sense that we talked about earlier in this class. There's a couple of algebraic expressions that I was originally going to talk about, but I'm just going to skip through these because I really want to get to the second part of today's lecture. So I just want to sort of skip through this and then basically say that there's a particularly easy way. Like if you have a ground set of size 2, so that means that you're talking about vectors of dimension 2, you can essentially construct an expression for the Lovász extension, which, arguably, 18.13 and 14, maybe that's an easy way of seeing it. And that's just sort of, in some sense, a closed form expression, although there is a min in there, so there's a one conditional. But if you're, for example, interested in plotting this as a function of W1 and W2, this might be an easy way of doing it in say, MATLAB or something. And this is true for any Lovász extension, again, when m is equal to 2. Okay? And to do that, I'm going to skip this. There's actually a lot of stuff I'm going to skip in this initial thing. Let's just go through here. Oh yeah, so this is an important slide. So basically, whenever it's the case, again in 2 dimensions, when W1 is greater than W2, then the Lovász extension is just this. This is just using one of those formulae. And then we can actually look at a particular point. So W is a continuous vector. And you can take the point 1, comma 0, which is a point in R2, and divide it by f of 1, which is equal to this. And any W that's defined in this way, the Lovász extension gets value 1. Okay? Has value 1 on that W. And similarly, if we take the point 1, comma 1, and divide that by f of the ground set, which in this case is 1 and 2, we get another W, which is also evaluated at, which also evaluates to 1. Okay? And you can just see that by looking at, just by plugging these guys into 18.15. If it's not immediately obvious, you just do it, and it's just a little bit of algebra. And then similarly, or symmetrically, when W1 is less than or equal to W2, we have other expressions that evaluate to 1, namely this point, which again is 0, comma 1 divided by, so it's like it's whatever this point is. It's like the first coefficient is 0, first coordinate is 0, and the second coordinate is 1 over f of 2. Then in that case, we again have f of w is equal to 1, f tilde is w, and then here's another point. And so what this allows us to do is look at contours of the Lovász extension, because the Lovász extension in general is sort of hard to visualize, especially in high dimensions. And so what we can attempt to do is try to look at contours and other aspects of visualizing the Lovász extension. We know it's going to be convex, we know it's going to be polyhedral, but we know also it's a special convex function. It's positive homogeneous and has all these other properties. And so we can actually look then at contours, which are basically W such that the Lovász extension is evaluated at 1. In particular, we're going to look at it and mark certain points which correspond to the characters, which correspond to sets A, and the points are going to be characteristic vectors of A times 1 over f of A, which is exactly what we saw here, 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 and here. So that all corresponds to this stuff down here. Okay? And where, in each case, the Lovász extension is equal to 1. Now, this is essentially from Francis Bach's paper, and I further annotated a little bit. But basically, the idea is that we're plotting the Lovász extension in R2, and the blue line, the thick blue lines, correspond to the contours where the Lovász extension is equal to 1. Now, this is true for any Lovász extension, any two-dimensional Lovász extension. It has this sort of shape to it. And so this sort of gets a sense of maybe what the Lovász extension looks like. In 3 dimensions, it's hard because as soon as you have 3 dimensions, like the Lovász extension gives you a value at every point in R3, and that becomes hard to visualize. But what we can do is make additional assumptions about the submodular function and look at certain projections of the Lovász extension that, based on the assumptions of the submodular function, don't change things. And in particular, what we're going to do is we're going to take any submodular function, f prime, and we're going to take a point in its base, right? X is going to be in its base. Then we're going to subtract off the point in its base from f prime, and we're going to get a submodular function f, right? It's just submodular minus modular. Now this is one that has the property that f of e, the ground set, f of e, f evaluated on the ground set is going to be 0 because we're taking x on the base, right? It's still submodular, of course. And in fact, all we've done is sort of shift things around a little bit. So again, the inherent structure and the interaction and as we've been arguing all quarter, that doesn't really change the nature of the submodular function at all. And then when we use this property, this strange property, where f tilde of w plus alpha 1e is equal to f tilde of w plus alpha of e, basically f of e is equal to 0. So what this means is that the Lovász extension is identical every time we every time we move up and down this axis. So it's a little bit hard to draw, but I'm going to try to draw it anyway. I'm not a very good drawer, but let's say that these are the 3 axes, and let's say that you take this point here. This is alpha times 1e. Okay. Then if you take slices, these planar slices, like these are supposed to be all planes that are perpendicular to alpha times 1e, the Lovász extension on those planar slices are identical. If you were to sort of come up with a two-coordinate system. So then what we can do is we can actually look at contours in those planar slices. So make sure that this is clear. So we're taking vectors. We're taking like the vector alpha times 1e, where this is the all one vector. And then we're taking planar slices orthogonal to that vector, and that's what these guys are, p, right? And then what we're going to do is we're going to look at contours on those planar slices. And hopefully, and then since it's going to be a function of two coordinates, which are the coordinates on these planar slices, each planar slice of which it doesn't matter since the contour is going to be the same, thanks to the fact that we've normalized the submodular function in this fashion by saying that f of the ground set is equal to 0. And so when we do that, we can in some sense look down at the contour plot and look at contours where on these planar slices where f of where the Lovász extension is equal to 1. Okay, and the reason, and then we find everything, at least from the perspective of contours, we find everything about it because as we move up and down, as we change alpha, move up and down this vector 1e, we're looking at different planar slices. We're not actually changing the contours in this case. And so here's one example of it. So again, the origin is here, and so it's a little bit, like I said, it's a little bit tricky to see, but here's essentially the three axes. And then we've got W1 is equal to W2, which is like the plane coming out of here. Maybe W1 is equal to W3, which is the plane coming out of here. And then W2 is equal to W3, which is the plane coming out of here. And that's my beautiful picture. But again, this is sort of looking down. Without 3D glasses, hopefully you can visualize this, but it's sort of like we're sitting at a point on alpha times 1e looking down at the origin. Okay, we're in 3D. We're at a point alpha times 1e looking down at the origin, and then we're looking at one of these planar slices, and we're looking at contour plots on these planar slices. And the contour plot in this particular case shows where the Lovász extension is equal to 1, which are these blue lines. And then we've partitioned R3 based on the different orderings, the 6 possible orderings of W1, W2, and W3. For example, this area here corresponds to W3 greater than W2 greater than W1. And this area here corresponds to W1 greater than W2 greater than W3. So there's 6 such partitions that corresponds to the 6 factorial possible orderings of, the 3 factorial possible orderings of a ground set of size 3. Okay. So everybody get the geometry of this kind of, hopefully? A little bit? It's a little bit tricky. But what one can do then is that, this is done for this particular, this is a submodular function. This is just a nice way of writing it, and it gives us a Lovász extension of this form. So it gives us the Lovász extension for these various different submodular functions. Here's one Lovász extension which corresponds to the total variation. This is the submodular function, and it corresponds to the total variation Lovász extension. Now, total variation you might be familiar with if you've done anything with computer vision, and because it's this is what we're going to talk about, because one of the uses of the Lovász extension in machine learning is essentially as constructing a structured norm. And so for this Lovász extension, for this submodular function up here, we get the total variation as the Lovász extension, and then this is essentially the way it looks. This is the contour, this stuff over here. Again, looking down from this vector, from this vantage point of vector 1e, alpha times 1e for some alpha. Okay. Total variation is something that's been used for a long time. I mean, here's an old paper from Rudin that talked about ways of doing image denoising, where you have an original image here, and then a noisy version where maybe you add Gaussian white noise or something, and then you use various different norms to try to sort of help, maybe in a Markov random field or something. You use different norms to sort of reconstruct to denoise the image. And if you were to use like a 2 norm, you get something like this. But if you use total variation, you get something like this, which looks, arguably much better. I'll talk about this in a minute. Again, because I want to talk about how the Lovász extension can essentially be defined usefully to construct a norm, useful in machine learning. When we have a submodular function has this form, which is just a concave composed with a modular function, then f is submodular. If we define mj to be the cumulative sum over the first j elements of m of ei, okay, where then essentially we get that where ei is sorted according to w, where w is going to be given, then we get that the Lovász extension has this particular form, okay, which is basically just the sums of the weighted differences of the concave function evaluated at these cumulative sums of the weights. And in particular, if we have a really easy concave function, then the Lovász extension is very simple. There's no, the ordering doesn't matter since every ordering has the same cumulative sum. So it's basically just the weighted sum of g I minus g minus 1. Now, of course, the I still matters because you're still renaming the ei based on the ordering in descending order according to w. Okay, so this is critical. But other than that, it's a very simple form. Okay. Cut functions. I'm going to go through these fairly quickly. These are not immediately trivial to see, that one can construct a very, very simplified expression for the Lovász extension. Like it takes a little bit of work, a little bit of algebraic work, to see that you can get simplified expressions for the Lovász extension. But you can do it, and in such case, you get very natural-looking functions. Like this kind of function here corresponds, equation 18.20, corresponds to something that seems to say that, well, you're going to penalize instances of w when wi is greater than wj, but whenever wj is less than wi, you're not going to have any penalty at all. So this seems like to be giving something like isotonic regression, which basically says I want a regression. I want to essentially have the coefficients be monotonically changing, right? So it's also sort of a form of total variation. There's a number of others that I compiled. Well, actually, I should say Karthik, former student in this class, compiled these additional Lovász extensions. And I think it's a good exercise to go through and try to derive these various ones. Okay, so let me just pause and see if there are any questions, because I want to now talk about a recent application in machine learning of the Lovász extension, which I think is important. And since we do have machine learning as a title in this course, I do want to say something about machine learning. So are there any questions about the Lovász extension at this point? Okay, so I think this next application is sort of a really killer app for Lovász extension. It's a killer app for submodular functions in machine learning. Basically, I think most people are familiar with supervised and unsupervised learning. I'm just going to very quickly go through this and say, let's say that you have a training data set which consists of xy pairs, where y's are a label and x are a set of input features. And let's say the supervised learning problem is essentially to solve w in this fashion, where we have a loss function L, which might be a squared error or something, but we want to penalize w in some way, and so we have omega of w, which is like a penalty or some sort of norm on w. And if it's the case that the loss function is the squared error and everything, that this basically equation 18.21 turns into a convex optimization problem. So machine learning, supervised learning can be seen as a convex problem. And this also, you can, if the loss is a hinge loss function, you get support vector machines. And if omega is the L2, is the 2 norm, right? Now there's instances where you might have multiple responses, so that rather than say y being just a scalar, y might itself be a vector of length k, in which case you get you have a matrix of weights, and so you have a sum over k. The key difference here is that you've got a sum over k, and then you have a norm on each one of the k's. Okay. But there's also the case where you may not even know the x's. So this is sort of unsupervised learning, or maybe dictionary learning, forms of dictionary learning, where what you're given is essentially a set of responses. And what you're trying to do is both learn the dictionary, which are x's, and w. And maybe you have a norm on w. And maybe you have certain properties that you want these things to have. And basically, in each one of these cases, I mean, again, without going into a lot of details about this, we have some sort of norm, right? And so what we're going to really talk about is the norm and ways of parameterizing the norm. And it turns out that one can parameterize the norm with a submodular function via the Lovász extension, which is, I think, really, really cool and interesting and applicable. And I think we're only beginning to see the applications of this. I've only seen one so far. So let's first of all talk about the p norm. So here's the p norm, which can include the 0 norm or the 1 norm or the 2 norm or the infinity norm, all these different norms. And these essentially they all have this form where basically we're summing up the coefficients of w, raising it to the p, and then taking the pth root of all of the final sum. Okay. The 1 norm has become very popular over the past 14 years now, I guess. Is that how long it's been? I mean, you started hearing about lasso regression in like 2001, 2002. And we like sparsity for a variety of reasons. It gets rid of things that we don't want. It's efficient from the perspective of computation, assuming you can do sparse computation. There's applications in compressed sensing and sparse regression, and sparsity is nice for many, many reasons. Another form of sparse norm, as I mentioned, is the total variation norm. And it takes the following form, where what we're doing is we're taking the sum of the absolute values of the differences of the coefficients. This is sort of the one-dimensional total variation norm. But there's also like a two-dimensional total variation norm. And what this really does, equation 18.24 does, is it basically says that if you're saying that successive or nearby points, you have a absolute value over them, you're basically asking the differences to be sparse. You're asking for very few differences. And when you're trying to do things like image denoising, this is exactly what you want. So you have an image on the left that's been noised, but that's noisy, and an image on the right that's cleaned up, because real images tend to not have very many places where you have significant differences. And unlike the 2 norm, the 1 norm really prefers to sort of get those differences down to 0 when it's done in the total variation framework. We in general, why should a norm be convex? Well, we like convex functions because they are relatively easy to optimize, and we know that they have a global solution. Now here's the key. This is, if you haven't been paying attention or if you think this is old, this next slide is really important for understanding why submodularity is useful for constructing a norm. So we defined earlier this sup operator, right? So the sup is basically a 0-1 vector, right? And it basically, in some sense, sort of counts, or it sort of indicates the points at which w is non-zero. Okay, so sup is like if you count the number of ones in the sup, those correspond to the degree of sparsity, or to the degree of, or lack thereof, really. As sup gets bigger, the size of sup gets bigger, it becomes less sparse. Okay, and so therefore, for constructing sparsity, you might take like the 0 norm. Which I guess the 0 norm is really like, this isn't exactly right, but it's like there's a sum over here. There's a sum over the items in sup, okay? And so that basically says the 0 norm is something that says, well, I don't care how big your coefficient is. I'm treating basically 0, anything that's non-zero I'm treating identically as being present, and anything 0 I'm treating identically as being not present. And when I use the 0 norm, basically I'm saying I want to have as few non-zero coefficients as possible. But as soon as it becomes non-zero, no matter how small it is, I'm paying a price. I'm paying an additional price of 1 for that non-zero coefficient, right? And now the 0 norm is, as I think most people know, minimizing this is NP hard. And so what we often will do then is to optimize the tightest convex relaxation. And I was going to have a figure of this, but let's just, so if this is W here, here's some axes, and here's W. And so what the 1 norm does, the 0 norm does, let's just, let's just do this for a minute. Let's just say this is -1 and 1. I'm looking forward to not having that bell anymore. Our bell. So essentially, we're going to have a penalty of 1 for all non-zero guys, except it's going to have open here and there. And then as soon as we have coefficient 0, we're going to have a penalty of 0. Okay, so that's the 0 norm, right? Now the convex envelope, or the tightest convex relaxation, is the largest convex function that lower bounds this norm, right? And I'm going to draw this in, let's draw it in blue, and that's going to look like this, right? So the blue one is the 1 norm, and the green one is the 0 norm, right? And so what we do, it's a reasonable surrogate, right? Because it says, well, I prefer to get, and maybe I'm sort of semi-differential. At least I can construct subgradients, and I can do reasonably nice things, unlike in the 0 norm, where there's no hint as what to do when you're not 0. Whereas the 1 norm, at least there's some hint that you want to sort of move down towards 0 when it's the blue case. Okay. So the 1 norm is the tightest convex lower bound, or the convex envelope of the 0 norm. Okay. But on the other hand, the 0 norm is sort of not so good for a variety of, for the following reason. So if we take the 0 norm or the 1 norm, or even any of the p norms, each non-zero element has sort of the same degree of penalty. So let's say element 5, it becomes non-zero, so then you pay a penalty of 1. And element 7 becomes a penalty of 1. But most importantly, the penalties don't interact. What if it was the case that if you suddenly make element 5 1, element 7 becoming 1 is much cheaper? Like maybe you're saying, I don't care if element 7, as long as if somebody insists that element 7 has to be non-zero, I don't want to pay a price for element 7, since things come in blocks or in bundles. Or maybe there's some sort of diminished cost. That seems like a job for submodularity, doesn't it? That maybe groups of guys together should have joint interacting costs for being non-zero. And so how do we do that? Well, we know we've got a submodular function, and we can, let's say it's a polymatroid function, and we've now gained this great intuition about submodular functions, and let's say that we take f of the sup of w, right? So basically the cost of w is basically the sup, the non-zero elements of w, and the submodular function applied to that. So that exactly is what we would like to do, right? Because if a particular element, say 5, becomes non-zero, the sup turns 1, and then the submodular function says, oh, well, if you're 1, I'm going to allow element 7 to be 0, to have 0 cost, 0 additional cost. So you're free, w is free at element 7 to also be non-zero. Okay. Now, on the other hand, there's the same problem, which is that this is difficult to optimize, right? It's this very difficult problem. But on the other hand, what we can do is take the convex envelope of this thing. That's hard to optimize, but it turns out that the Lovász extension is the convex envelope of the submodular function applied to the sup of w. And this is shown in a couple of different sources. But basically what this means then is that the Lovász extension, and it turns out the Lovász extension of the absolute value really of w, it turns out it is a norm. It's a convex norm. And it's the convex envelope of the submodular function applied to the sup. So therefore it has the same sort of properties that it's analogous to the L1 being a surrogate of L0. The Lovász extension is a surrogate of the submodular function of the sup. So what you can then do is, let's say you have your structured convex optimization problem. And when you design or you select or you produce in some way a matroid rank function. I mean, when we have all of these tools now we can use to design submodular functions. We have the dual matroids and the transversal matroids, and we can take matroids which are from a linear space, representable matroids. We have so many tools to represent structured convex norms. Well, at least costs of non-zero elements of vectors, and then we can take the Lovász extension of that, and then that'll give us a convex norm, which we can then add to our problem. Okay, and there are many examples of this, like total variation. Here are some very, very simple ones. So, like the submodular function cardinality of A is the L1 norm. The Lovász extension is the L1 norm. Okay? And if we take a modular function, then the Lovász extension is the weighted L1 norm. So, coefficients being non-zero don't have to have exactly the same cost, but they're still not interacting, which makes sense because it's a modular function we're taking the Lovász extension of. Note that the L2 norm, you can't generate easily the L2 norm with the Lovász extension because the Lovász extension is inherently polyhedral. The 2 norm, on the other hand, isn't really structured in the same way, right? Because the 2 norm basically says it's the square root of the sum of the squares. So if any one element gets big, or any other element gets big, it doesn't, there's no sort of, maybe in some sense there's a global interaction in the sense of via the square root function, in the sense that the norm, the overall cost starts diminishing. But on the other hand, there's not really, if one gets big or the other gets big, there's no distinguishing. You can't say, well, if element 13 gets big, I want element 7 to be cheap. But if element 14 gets big, I don't want element 7 to be cheap. That can't happen with any of the p norms. Whereas with a submodular function, it can. And moreover, the 2 norms are always monotone in not taking the pth root. Right? So if you take the 2 norm or the squared 2 norm, they're monotonic related to each other. So in some sense, the square root doesn't really do much. I mean, it does give you a diminished cost when you're using it in combination with a loss function, but it doesn't really, have the sort of nice sort of interacting type of flavor that we can get with a convex envelope of a submodular function of the vector W. So what this means, however, is not all norms are from the Lovász extension, but that's not surprising since not all convex functions are a Lovász extension of some submodular function. I mean, not all convex functions are positive homogeneous, for example. Not all convex functions are polyhedral, of course. But one can, for example, mix together norms. You can do a mixture of a 2 norm and a Lovász extension or other forms. And so it basically, like I said, opens the doors and makes accessible a very large number of different constructs for constructing norms for your machine learning problems. Okay. So like I said, I think that's a really good application of the Lovász extension in machine learning. But what I want to do next is talk about the min norm algorithm. But let me pause for a few questions to see if there are any at this point. Everything makes sense? Okay. Okay, so that's good. We're making good time. So the next set of slides I'm going to go a bit slower because this is going to be important for your final project. So please, let's all reset each other. If I mean, all of the stuff, you need to understand the Lovász extension to some extent to understand this stuff. But on the other hand, it's not that critical. So let's just sort of reset and ask questions if you have any. Okay. So first of all, let's do a couple of review slides from lectures 12, 15, and 16. The first review slide is again showing this min-max duality thing that says that the rank, this is a review that we've seen many times, that the rank of X, which is the largest component sum that's independent, the largest subvector which is independent in the polytope is equal to the min of the submodular function. And that basically gives us this really important duality property, which was used to prove that the minimum norm point can give us the solutions to the submodular function minimization problem. On the right-hand side of equation 18.6, we have the submodular function minimization problem. And here's the minimum norm point definition again. So here's, again, certainly that theorem. The definition basically of the problem is to find the smallest 2 norm in the base. Okay? So we have to be in the base. This is the squared 2 norm. And X star is the optimal solution. So X star is the solution to equations 18.13. And it's unique. There's only one solution because we have a strongly convex function that we're minimizing. And X star is called the minimum norm point. And the algorithm to find this is called the minimum norm point. So what we've done in the past is we've proven well, first of all, we've defined several additional constructs, y star, which is basically just the it's a vector where all positive elements have been truncated to 0. And we defined a minus, which is the set corresponding to the elements which are strictly negative, and a naught, which is a set corresponding to the elements which are non-positive. And we have this relationship and all this other stuff. And basically we have the following proof. That y, first of all, y star is a maximizer of the left-hand side, and since we have the equation sitting here, this is this reference problem that I've been telling you. This is the left-hand side that we're talking about here. So y star is a maximizer of this, right? And a minus is the minimum, is the unique minimal minimizer of the submodular function, and a naught is the unique maximal minimizer. Now, this is just the first page of the proof, and a couple of lectures ago, I think 2 lectures ago, we proved this in detail. Okay. There's an alternative proof that some of you well-versed in convex duality might prefer, and that basically is the following. It says that the right-hand side, which is the maximum of the negative of the squared 2 norm, subject to x being in the base polytope, is the convex dual of this convex optimization primal problem. And what this problem is, this is minimizing the Lovász extension plus the squared 2 norm over all W. Okay, so this is actually, equation 18.25 is really essentially related to a proximal method for minimizing the Lovász extension. Now we don't have time in this class to go into proximal methods. Those of you who are taking Miriam's convex optimization class have probably talked about that. Is that correct? I'm sure. Maybe. But in any event, there's a really nice, very, very recent almost medium book length survey of proximal algorithms and proximal methods by Boyd and Parikh, and that I've read some of it. It's really nice, just like everything coming from Boyd. It's really nice. But if you're interested in sort of understanding equation 18.25 again, 18.5, I would suggest reading that. But basically, it's interesting that you can sort of derive by strong duality, strong convex duality, again, the proof that the minimum norm point solves the, and proximal methods solve the submodular function minimization problem using the fact that when we've got the minimum of the Lovász extension, we can essentially construct the minimizers of the submodular function. So what we're going to really be doing, the minimum norm point algorithm, is really then an efficient algorithm for minimizing the dual of the Lovász extension, or the proximal variant of the Lovász extension. And that's what Wolff's algorithm does. Okay. And as we're going to see, the running time is actually unknown. It's currently an open problem. For the longest time, the running time of the simplex for linear programming was unknown. The minimum norm point is reminiscent. It's wistfully reminiscent of the simplex algorithm. For those of you who are familiar with it, you might be reminded a bit of it. But I think that that's an interesting thing. The other thing, just to make sure that's clear, like this dual, we're maximizing the negative of the 2 norm. What we're really doing is, it's the same as minimizing the 2 norm, square 2 norm. So it doesn't matter. So we're, but really, when we think of it in convex duality, it's minimizing one side and maximizing the other side. And I thought this is a slide I could easily have done earlier. This is the particular example of a 3D base polytope. So this is something that is listed in Fujishiki's book very early on. But I just want to show you that the base can be pretty interesting, even already in 3D. So remember, what we're talking about is if this is the submodular polytope there, we're just talking about this one little bit here. Although now this yellow bit is now in 3D, okay, for a ground set of size 4. Okay. Now the submodular function in this case is just this. So it's g, which is a concave function of the size of x. And this concave function is constructed from a sum. Okay, so in this particular case, this is the base polytope. Namely, the points in R3, well, I should say, it's really the points in R4 projected into R3 such that x of E is equal to f of E, or I guess V in this case, since we're using V as the ground set. So you could think, like, for example, here's the origin down here, maybe. I don't know where the origin is. Let's say the origin is here. The minimum norm point is going to be here, x star, maybe. And it's going to be orthogonal to the face that it lies in. So it's either going to be orthogonal to the face that the minimum norm point lies in, or it might correspond to a skeletal edge, or it might correspond to a vertex if things are very strange and you win the lottery. But in general, it's going to be orthogonal to the face, okay? Because of the polyhedral aspect of that. Actually, that's not really true, is it? Because it's going to be if it's on a face, it's going to be orthogonal to the face. But if it's on a vertex, it's going to be obviously not orthogonal to any of them. So it is really true. Okay, so the other thing I want to mention is, so in the Fujishige and Isotani paper, they have this variant of the min-max theorem, which can also be used with some minor modification to prove the min-norm point theorem. Just wanted to offer a little bit of a proof for this. Basically, what this is saying is that the min of the submodular function is equal to the max of x minus of E. And what x minus of E is basically, it's the component sum, but again, where we're truncating all positive elements to 0. Okay, so it's all some x in the base. And the way we can get this now is based on the Lovász extension. So we start off by taking the minimum of the submodular function, which we know is equal to the minimum of the Lovász extension, which then we can plug in the linear programming definition of the Lovász extension. We have all these different ways of using the Lovász extension. So the definition of the Lovász extension we're plugging in is this one. Okay, and then we're just minimizing over that, which is this part here. And we know that that's, we saw that that's equal to, the Lovász extension can be obtained by maximizing over the base rather than just the polytope, because remember the base is always dominates all points in the polytope or in the polyhedron. Then we can swap the min and the max. Does anyone know why we can do that? If you don't, I have a slide on it in a few minutes. Or actually in 1 minute. So let's go. We will very easily see why that swapping is valid. But once you have this, once you get that swapping, then you immediately see that to minimizing, if we just look at this part, the inner min, W is in the hypercube. So if there's any x that's negative, we're going to set W to be 1. If any of the elements of x are negative, we're going to set the corresponding W to be 1. And if any of the elements of x are positive, we're going to set the corresponding elements of W to be 0. So basically what we're doing is we're just summing up the negative elements of x. And that's going to be the min for any x in the base. And so we get this. That's the result. Now why can we do the min-max swap? I mean, it follows from strong duality. Basically, we've got this function g of x, g of wx, which is a dot product. W is in the hypercube, x is in the base. Then for any pair of wx in the hypercube and the base, we've got g of x, w, which is just this dot product. And if we can maximize over points in the base, and that's going to make it bigger, right? And then we can minimize over points in the hypercube, and that's going to make it smaller. Right? So equation 18.32 is always true for any w and x. Now, this function here can be seen as a convex function of w, right? And this function here can be seen as a concave function of x, right? So then when we so then when we minimize this convex function of w, and we maximize this concave function of x, we still have the inequality because 18.32 is true for all points x and w, right? But thanks to the fact that gxw is linear, we have strong duality, which means that they're equal. And when you see once that we've got that equal, all we're doing is just swapping the mins and the max. So it comes thanks to convexity. Okay, so min-max swapping is totally fine here to do. Okay, so the other thing I want to mention is, again, minimizing. We're going to need to minimize a point in the base. Okay, and we've been talking about maximizing points in the base, but does minimizing w transpose x such that x is in the base polytope, is the minimum going to cause us any problems? Since we've so far talked about maximizing w transpose x such that x is in the base. So the greedy algorithm we saw solves the maximum problem, right? The greedy algorithm, in fact, will solve this, which I've already said. But it turns out that if you take, since this will solve this for any w, the greedy algorithm will solve it for any w, positive or negative or both, right? We can essentially take the negative of w, construct the max, and then negate that, and then we get the min. So therefore, the greedy algorithm also constructs the left-hand side of 18.37. Now, the left-hand side of 18.37 is going to be the thing that we're going to need for the minimum norm point algorithm. The greedy algorithm in this case is basically, rather than sorting the elements in descending order, we just sort them in ascending order. Since if we take the negative of vector, it's the vector w, we're just sorting them in the descending order. So it's exactly the same thing. So this shows that this guy, which we're going to need in the min-norm algorithm, is perfectly accessible to us by Edmonds' greedy algorithm. Doesn't matter. Now, one thing I wanted to mention is why can you do this for any w? So like w positive or negative, if you're concerned about that, then here's a very simple way of showing it. So let's say that f is any arbitrary submodular function, and let's normalize it so that f prime is a polymatroid function and m is some modular function. You could use the totally normalized variant of the modular function, but it doesn't matter. So let's assume that f is polymatroidal, and so what we're doing is that the base of f prime is going to be in the positive orthant, right? So then when we want to maximize, we're going back to maximizing this for x in the base. This is just the same as maximizing this, and everything to the right is just defining what it means for x to be in the base. Basically, this is what it means for x to be in the base. And then we can plug in our f prime minus m definition of f, where we get that. We can move m to the other side, and we get that. And then what we get is this sort of variant of the problem, where what we're doing is we're maximizing this subject to this set of constraints. And where we've removed Wm from the problem. Since W transpose times M doesn't affect the maximization problem. Okay? So now what we've got is essentially a maximization problem just using a change of variables where y is in the base, where the base is in the positive orthant. And then the proof that we did before is where the basis of the positive orthant still holds. Okay. There's one last thing we need, which is that this duality proof, we assumed, if you remember from a couple of lectures ago, we assumed that if w was negative, what we would do is we'd stop. Right? We'd essentially set all of the x's to 0 thereafter. Now, it's only the case that you get a point in the base if you totally order the elements. So in other words, you have to take a sum of differences of the submodular function for all elements, not just the ones for which w is greater than 0. Okay? So what we do in this case, when we go back to the theorem 12.4.1 in lecture 12, and this is the right reference. I made sure this is correct because this is an important theorem to go back to refer to, is we don't actually stop at W when it goes negative. We just go ahead and order things in descending order. So even if it becomes negative, okay. And then the only thing that is different in the proof to show that it's optimal is to relax in the dual the constraint that y is greater than or equal to 0. And will be dual feasible. The resulting solution is dual feasible without this constraint, and we still have convex. We still have strong duality, and so therefore this is the optimal solution to this problem, the one that I've highlighted in pink. And then continuing on, when we combine the solutions back together, we get that the resulting solution here is equal to the optimum of this problem. So this is the problem for any W, which may be positive or negative, and any submodular function, which is not necessarily polymatroidal. So it's just sort of closing. It's a couple of little nagging gaps that we haven't really officially closed yet in this course, but now that's closed. That's addressed. Okay. And also shows how to run the greedy algorithm when W is arbitrary and when the submodular function is not necessarily polymatroidal, so that the base is not in the positive orthant. Okay. A couple of other definitions that we will need. So h of x is going to be defined as the hyperplane that's orthogonal to the line from 0 while also containing x. So let's just draw a picture for this. So here's our axes. Here's the origin down here. And let's say here's a vector x. And the h of x is going to be this thing. Where it's orthogonal. So it's a hyperplane that is orthogonal to the line from 0 that is also containing x. And you can see it, I mean, it's a very simple thing. Any set y such that x transpose times y is equal to th is orthogonal to the line. But if we just want it to also contain x, we need to have this be true, which is basically just saying that it puts a constraint on C to be equal to the norm squared. Okay. And so what we can do, what we're going to see is we're going to use this for a number of things, because we're going to have polytopes out here, or more specifically, we're going to have like a polytope here, where that's going to be a supporting hyperplane of the base, right? And what we can do is, like, once we find a point that minimizes the 2 norm that's also separating the polytope from the origin in this way, we're going to be able to show that we've got the minimum norm point. Okay. Another definition is the convex hull. Raise your hand if you need me to define what the convex hull is. I don't think so. The affine hull, however, is slightly different. I mean, the only difference between the convex hull and the affine hull is that in the convex hull, we insist that all of the w's are greater than or equal to 0, all the coefficients. The affine hull basically doesn't have that requirement. So if you were just geometrically, I mean, it's useful to think of this geometrically. If you define 3 points, maybe I shouldn't do this. Let me just add another point. Should I define the affine hull, or does everybody know that? Raise your hand if you want a picture of the affine hull. Okay, I will do that. Add a page below. Okay, so let's say that you have 3 points. Okay, so the convex hull is going to be all of the points in the interior of this, right? That's the convex hull. But the affine hull is everything, basically. On the other hand, if we have these 2 points, the convex hull is just going to be everything between. But if you have 2 points here, say, the affine hull is just the line. Well, maybe I should draw it in this yellows. It's just this line, okay, going through those 2 points. So the affine hull is the line defined by the 2 points. So if you have multiple points that are collinear, then basically any two distinct of those points have the same affine hull. Just geometrically quickly. Another notation that we need is this notation, x comma y. So this is basically just the line between 2 points, x and y. So if this is x and this is y, it's really just the convex hull between the 2 points. Okay? And but we're using this notation to refer to that set of points. The other thing to note is that if we wish to minimize the 2 norm of a vector, we can equivalently minimize the square of the 2 norm of the vector, since they're monotonically related. So we sort of can interchangeably switch between, say, minimizing the square of the 2 norm or just the 2 norm itself. The square of the 2 norm is just the sum of the squares, right? So when we're minimizing, the min norm point is the minimum 2 norm, or it's also the minimum square of the 2 norm. In each case, we have circular contours. So like if you talk about a point here, points of equivalent 2, if this is the origin, points of equivalent 2 norm define, or point of equivalent squared 2 norm define a circle or a sphere. Okay, any questions on the setup, the notation? So some of you who have been reading the paper are maybe familiar to this, but maybe the notation we're defining is slightly more modern than what's in the Wolf paper. And hopefully between these lecture slides and Wolf's paper, you'll successfully produce an instance of the min-norm algorithm. So basically, Wolf in '76 developed an algorithm to compute the min-norm of a polytope, specified as a set of vertices. And then in '84, or I think actually probably a few years before, but in his 1984 paper, he realized that this algorithm can find the min-norm point of P4. Now it's kind of interesting because Fujishige and Isotani, I don't precisely know exactly why they did this, and I didn't get a chance to ask him that, but he knew this in '84 and he published this in this paper, Submodular Systems and Related Topics. So it's not like he discovered this in 2009, which is the date of the Fujishige and Isotani paper. He knew this a long time ago. And in fact, if you go back and look at the first version of his book from '95, he also mentions this in his book. But I think what happened in 2009 is they implemented it and they tested it and they started looking at this algorithm in a number of different ways. And it seems to be, in practice, the fastest, or at least among the fastest, general purpose submodular function minimization algorithm. Now obviously, if your submodular function is really graph cut, you're not going to use the min norm point to minimize the graph cut. You're going to run a min cut max flow algorithm. And if you have a particular type of graph, you're going to use something even more specialized. But let's say that you have a black box submodular function. You don't know anything about it. You want to minimize it. Or let's say you have a submodular function which is defined in a way that doesn't lend itself to specialized implementations. Then the min norm seems pretty good. And that's what you're going to be implementing. Or have already done that. Raise your hand if you've already finished. Okay, so you've got a set of points. So this is what the min-norm algorithm does in general from '76. So Wolf in '76 does not define submodular functions. It was Fujishige who realized that it could be applied to submodular functions. Wolf was just talking about a general optimization problem of the following form, where you have a set of points, P1 through Pm, where each of the P's live in Rn, and you want to find the minimum norm point in the convex hull of P. Okay? So we recognize this problem as, P is really the base polytope, and the convex hull, these are all of the extreme points of the base polytope. So basically what we know as from our being submodular people here in this class, we know that the base is specified by an exponential number of polytopes, right? Which might seem like it's a potential problem here because when m is exponentially large, that may be problematic, but we'll get to that. So Wolf's algorithm is guaranteed terminating, as we will prove in the next hour. And explicitly, which is particularly nice about this algorithm, doesn't explicitly actually produce x, but represents x by convex combinations of the points in P. So what you're doing is you're keeping this vector of convex coefficients. Okay, so, and that's how you're representing x. Since any x inside of P can be represented by a convex combination of extreme points, right? And so therefore, it's equivalent mathematically to represent both. The algorithm also always maintains, this is like the active set, right? This is what we said on the other slide. Q, which is a subset of vertices, and that Q is always assuredly affinely independent, which is something also that we need to prove. But this is just a property of the algorithm. It's an invariant of the algorithm in today's language, or maybe the language of algorithmic proof checker theorists. So Q will always be affinely independent. And you know what affinely independent is, right, now. The only difference, so that basically means that, so there's one other thing. So when Q is affinely independent, the minimum norm point in the affine hull of Q is really easily found. In other words, this problem can be solved basically, as I'll say it briefly, it can be solved basically using either matrix inversion or linear solver. It's just a linear equation, linear matrix equation. So if you have, and in your code, by the way, you might have questions about your code. You're free to use any C++ linear solver you can find online. Someone asked about MKL, so it's going to be running on a laptop, and you don't have to implement a linear solver. Or you can if you want to, or if you have one sitting around. But you do have to turn in the code, so you have to turn in whatever it is that you're using. And the linear solver is what's going to be able to solve this problem. And I thought actually in the Wolf paper, his description of how to solve this was pretty clear. So I'm not going to spend a lot of detail on that in today's lecture. So what the algorithm really does is it repeatedly produces a min norm point x star for the set Q. And remember, Q is guaranteed to be affinely independent. If once we've done that, it so happens that the weights of the minimum norm point in the affine set Q happen to be strictly non-negative, then basically it means that x, since the affine hull is always bigger than the convex hull, by the way, that should be something that's very clear. So the convex hull of a set Q is always smaller than the affine hull of Q, right? So if you find the minimum over here, and it turns out that it lives within there, then you've lucked out, and it turns out that you've also found the minimum norm point in the convex hull of Q, right? And if Q is auspiciously chosen, then that x that you found by solving an affine solver might in fact even be the minimum norm point over convex P, which is P is the original set of vertices of the polytope, solving the original problem. That's great when that happens, because that means you're done. And everybody wants to be finished, right? Because this is a contest. There will be a tangible prize for the person who has the fastest successful min-norm algorithm next Thursday. Now, one of the more expensive part of Wolf's algorithm is solving the linear optimization problem with a polytope, right? So, like, how do we do that, especially when there's an exponential number? This is in general, if there's an exponential number of points in the polytope, we're screwed. We can't do it. The minimum point algorithm is not viable in such cases. However, thanks to Edmonds, good old Jack Edmonds, thanks to him, we can actually find points in the polytope and do linear optimization over the base in log n time using the greedy algorithm. So suddenly he's made accessible this procedure. Okay, so here is now the algorithm in one page, and it took a while to squeeze the algorithm down to fit into one slide. And so what we're going to do is we're going to talk about this algorithm a lot over the next couple of slides. And because we're going to refer back to this, I'm going to keep one myself. I wanted everybody to have a printout it. And then if you're watching this on YouTube, it would be beneficial for you to print out this slide and have it next to you, because nothing we say after this will make any sense without having a printout of the algorithm sitting here. This is basically, this is all derived from Wolf 76, except like I said, this is a slightly more modern, maybe, notation. And it's formatted in LaTeX, and so therefore it's nice. I don't know. But I think this is actually a good time to take a break also. So why don't I pause, you just start looking at the algorithm, and then we'll continue after break. Okay, so like I said, it's advisable in the next set of slides for quite a while, actually, for pretty much the rest of today's lecture, to have a printout of the previous min-norm algorithm available on display. And I personally have one sitting here next to me that I'm going to be also referring to as we go through these slides. And we're going to be referring to individual line numbers, lines 1 through 16. So the first thing to mention is that the algorithm maintains an additional invariant, which is that x is going to x star. So we always assign x star. We assign x star in a number of places: lines 1, line 11, and in line 16. Those are the only places where we assign x star. In each one of those cases, we're going to ensure that x star lies within the convex hull of Q. Okay. Now, in line 1, it's true. Why is it true in each of those cases? Well, Q is just going to be equal to the single point x star, so therefore it's in the convex hull of Q, which is just one point. In line 11, it's also going to be true because if you look at line 10, we check if x naught is in the convex hull of Q, and if it is, then we assign x star again with the x naught. And then lastly, it's also true in line 16, since when we do this minimization in line 14, we get y, and then what we're going to do is we delete from Q the points not on the face of conv Q where y lies, and so we're guaranteed where if y is lying on a face, we're not going to delete the points which define that face, because that's the face where y lies, and so therefore we're still going to be the case that x star is in the convex hull of Q after line 16 is done. Okay. Now the other thing to note is that if we take any x star in the convex hull of Q, okay, we have, so the x star meaning, the x star is meant to be just the name of an x. It's not meant to necessarily have any optimality property here. First thing is that the 2 norm of x star is going to be lower bounded by x in the convex hull of Q, of the 2 norm, the minimum 2 norm of the x in the convex hull, which is also further lower bounded by x in the affine hull. Again, because the affine hull is bigger than the convex hull. So it's something that's important to keep in mind. Now, the algorithm, hopefully you've had a chance to look over it a little bit. And I think everywhere is pretty straightforward except for the following 6 spots. Lines 4, like how do we find if h of x star, remember h is the hyperplane that's orthogonal to the vector x star that contains x star. So how do we see if that separates P from the origin? And then also line 6, choose an x hat on the closer side of that hyperplane. It turns out that x4 and x6 are going to be solved by Edmonds' procedure. It's going to take us a while to see that. But the 4 and 6 are done thanks to Edmonds. The other tricky bits, or potentially tricky bits, are lines 9 and 10. Lines 9 is going to essentially be this linear equation solver. So this is done in n cubed time. In fact, line 9 being done by a linear equation solver is how we get that the minor loop. If you look at the algorithm, you can see that, in fact, I should have mentioned this before. There's a major loop starting at line 3 and a minor loop starting at line 8. Because line 9 is going to be an n cubed operation, matrix inversion or linear solver, we know that the minor loop is at least n cubed. Okay. The big question about this algorithm is how many major loops run. That's why the complexity is unknown. We don't know how many major loops it takes. And if it's the case that the major loop runs n times, then we've got an n to the 4th algorithm. But as we will see, that doesn't always seem to be the case. And that's again assuming that the minor loop, each one of these guys is n to the fourth. But in any event, line 10 can also be solved, again, by that same trick, because what we're going to do is we're going to solve the linear solver by giving us the set of affine coefficients. And then line 10 is going to be solvable by just checking whether the affine coefficients are all greater than 0, greater than or equal to 0. And then the last bits that seem like they might be tricky is lines 14 and 15. And those, it turns out, are actually deceptively hard. It turns out that, again, thanks to the fact that we're going to be representing these points as convex combinations within Q, we're going to be able to solve 14 and 15 pretty easily. And again, I think that one is pretty straightforward, so I'm not going to spend too much time on 14 and 15. What we really want to do is sort of understand the algorithm a little bit more. And to do that, let's do a geometric example. So this is a geometric example that's taken from the Wolf paper, but where I've severely annotated it in many different ways. And I don't know if severe is usually a bad word, but maybe I should say I've pleasantly annotated it would be better. But in any event, we have this polytope. This is not necessarily a base. This is from the Wolf paper, so he's not talking about the base of a submodular function. So the polytope is defined by 3 points. Okay, the origin is down here. And we've got 4 concentric circles. All of the circles that we're going to draw are centered at the origin. And so what we see is that the minimum norm point is right here. Right? That's the one that's on this particular face. The closest vertex is P1. The next closest is P3, and the farthest vertex is P2. Okay? So there's the initial situation. So we've got the origin, and we've got these 3 extreme points of the polytope. Okay. First thing we do is what the algorithm in line 1 says to do is to choose the closest point, the closest vertex. And so P1 in this particular example, as we've chosen in red, is in fact that closest one. But in general, that itself can be done arbitrarily. You can choose any vertex. And in fact, when you look at the min norm for the submodular function case, you just choose any arbitrary vertex. You don't have to choose the closest one. Since that problem already, line 1 is hard. But as soon as you do it arbitrarily, it becomes easy. So then what we do is we set x star equal to P1 in line 1 of the algorithm. Okay. Q is just going to be the set of size 1. So that means that x is in the convex hull of Q. And then h of x star is this hyperplane, okay, green dashed line. And it's not a supporting hyperplane of the convex hull, right? So because the convex hull, what is a convex hull of P? It's basically the whole polytope, right? It's not a supporting hyperplane. It does not separate the origin from the polytope. So we move on to the else condition in line 5, right? So line 4 ended up being false. We move on to line 5. So we need to choose another point. And we need to choose a point x hat in line 6 that's on the near side of h of P1. And let's choose P2, which is this guy down there. Okay. And so then in line 7, we augment Q. And so now Q is now equal to P1 and P2. And you can see that the vertices are marked in red. The picture is sort of displaying in red what the current state of Q is. And again, like I said, we're always maintaining that Q is affinely independent. And you can see that Q is still affinely independent here. It's just a line. And in fact, in this particular case, all sets of vertices are affinely independent. But if you had another, and maybe this would be a better example if there were more vertices, so that there would be the possibility of not having an affinely independent Q in R2. But in this case, that doesn't happen. Now we construct the minimum norm point, which is R. So this is the minimum norm computed in line 9. So it's the minimum norm of the affine hull of Q. And so what's the affine hull of Q? It's going to be this whole thing here, right? And where does the smallest circle intersect that yellow thing? It's right at this green guy right here, this green point. Okay. And And that becomes x naught, which we're also calling it r. By the way, if this notation, I was realizing that this is probably confusing, but this isn't supposed to mean r of x naught. This is really supposed to mean that this is point r and x naught is currently equal to r. But it was too late to change this. So it should mean r equals x naught or something. It's not r of x naught. But it's also confusing because here we're using h of p1 where we really mean it's a function of p1. Here we're not saying this is a function. So all of these points, hopefully there's no confusion. The points are just being renamed. Okay? Is that clear to everybody? Roughly speaking. So much for a clear example of the min-norm algorithm. All right, so now Q is equal to P1, P2. And R happens to be in the convex hull of Q. So in line 11, so in other words, the test in line 10 is true. Okay? So then line 11, we do the assignment. And the other thing to note is that after line 11, we still have that X star, of course, is in P. But we also have that the 2 norm of the new X star is going to be strictly less than the old X star. And why is that? I mean, because if you look at that circle versus this other circle, we've shrunk the 2 norm. Okay. That's good news. Okay. So now we go back to line 4. And the condition is again false. Right? So x star is neither 0 nor, by the way, 0, if it's ever 0, you're done, right? Because that's the smallest minimum norm you can get. That's kind of a trivial finish point. So if the polytope contains the origin, then you're done. But you can see that again, the hyperplane, which is now x of r, is not supportive of the convex hull of P. So then we choose another point which is on the near side of the hyperplane in line 6. Okay, and there's only one last point to choose, and so we're going to choose P3. And so that guy P3 is now red, as you can see. And so now Q is equal to P, which is all of the points in this particular polytope, and that's equal to P1, P2, P3. So once we've done that, once we have this P, and we find line 9 again, and so the affine hull is basically all of R2. So now what happens is that we find the minimum norm point, and the minimum norm point is equal to this guy. So x naught is equal to 0 in line 9. But it's not in the interior of the convex hull. So the condition in line 10 is going to be false. So now we have to go to line 13. Okay, and line 13, the first thing we do is line 14. So what we do is we find y, which is in the minimum of the convex hull of Q. So the Q is everything, right? So basically, and then we take the line between x star, which is this guy up here, and x naught, which is down here, that intersects the convex hull. So it's basically this yellow region right there. So it's this yellow line here is meant to be this little bit. This bit here corresponds to this yellow line. Okay, and then if you take the minimum, the penalty is going to be essentially the distance away from x naught. So that's going to be, we're subtracting off x naught. In this particular case, x naught is 0, but in general we subtract off x naught in this particular case here. And so what we're going to get as a solution is point S, okay, which is also equal to y in the algorithm. And we see that y lies at the boundary of the convex hull of Q. Right? In general, that's going to be the case, because what's going to happen is, remember, so x naught in this particular case was in the affine hull but not in the convex hull. And since the affine hull is bigger than the convex hull, that's going to be big. That's going to be smaller, a minimum norm point. That's going to be closer in some sense to the origin than anywhere in the convex hull of Q. And so therefore x naught is sort of way down here, closer to the origin. X star is sort of up there, and there's this line between x star and x naught, and we're going to minimize it along that line towards x naught, and we're going to be at some face. And so it's going to be the boundary of whatever the convex hull of Q is. So we're getting in the right direction. And the other thing to note is that y has a smaller 2 norm than the current 2 norm of the current x star. And the reason why is because x star was a feasible solution here, right? Since x star is in the convex hull of Q, it's feasible in this minimization problem. And so therefore, when we get the new guy, it has to be less than it. Right? Why is it strictly less? Well, because x star was not in the convex hull of Q, so they can't be the same point. We must have that x naught and x star different. So it has to be strictly less. By how much? We don't know. That's the big question. Now, line 15, looking at this thing, basically says we delete the points from Q that are not on the face where S lies. So basically that means in this case we delete P1. So now we have our new set Q, which is just this guy and this guy. Those are the ones in red. But note that we haven't destroyed the property that Y, the solution that we did with the slightly larger Q, is in the convex hull of Q because of the way that we've deleted points, right? Because S is sitting here on this face, and we're not deleting any of the points in Q that define that face. We're only deleting points off that face, farther away from that face. And what's interesting is that those points that were deleted are never going to be added again. Because as we're moving closer and closer to the origin, those guys, there's never going to be a reason to add them, as we'll see. So therefore, in line 16, we add the new x star. And we're again, in this example, we're going to strictly see that the new x star is going to be less than strictly than the old x star. Okay. So do I have a picture for that? The new x star? Yeah, so here, I think this is going to be the new x star down here. And this is the old x star, and we're strictly better in this example. We're not at the minimum norm point yet. The minimum norm point is this light blue point. Okay, so we start off with Q is equal to P2 and P3. And so we go back to line 9. And in this particular case, what is the affine hull? It's this whole thing. But when we look at the minimum norm point in the affine hull, we're just going to get the blue point, which it turns out in this particular case is going to be the true minimum norm point of the whole algorithm. So therefore, line 10, the condition in line 10 is going to be true. We then go ahead and do the assignment in line 11 and break, and then jump back to line 4. Okay. Now in this particular case, h of t, this hyperplane is this whole thing, right? And it is in fact a supporting hyperplane of P. And so therefore, x star is the minimum norm point, and we return with the minimum norm point. And that's how the algorithm works. Okay, any question about the run through the algorithm? Okay. You're asking a lot of questions today. I don't know if I can answer all the questions you're asking. I'm being flooded. You will understand this in a week and a half. I guarantee you. So better than I, because I've actually never implemented this algorithm. But I would like to. Maybe I should take this class. So then I have to implement it. So anyway, so there's a couple of theorems that we need to prove to show that this algorithm is correct and that it terminates and everything. The first thing that we want to show, which is from Wolf's paper, is that if we choose some x star in the convex hull of P, it's actually the minimum norm point if it's the case that for all P, this inequality is true. So the way we should do that is let's start by assuming that x star is the minimum norm point, and let's say that y is any other point inside of the polytope, and define z. Oops, what is that? That's not what we want to do. I'm so glad I discovered the back button on this thing. Okay, I've defined Z, which is a convex combination of X star, with the point we're claiming to be in, or we're assuming to be in the minimum norm point, and Y. So Z is some convex mixture, and so since it's a convex mixture, it's also in the convex hull of P. Okay? And so then if we look at the norm squared of Z, which is just the norm squared of this convex mixture, that basically, just by completing the square, has three terms. The first term, the second term, and a third term. Right? Color makes equations clear. Right? Now the third term is definitely positive, or non-negative, right? The first term is definitely non-negative. The green term potentially might be negative, right? So the point is, we're claiming that X is the minimum norm point, Z is some other point, and if this is true, then Z must have greater than or equal to, I mean, it's a unique norm, right? So if it's the case that Z is any other point and Z is distinct, then it must be the case that the norm of Z is greater than the norm of X. And so the only way for this to happen is to make sure that the yellow, green, and red quantities are all positive. But it's possible for the norm of Z to be less than the norm of X star for very, very small theta. So if we can take theta very, very small, what ends up happening is that if this guy ends up being negative, theta being small is the square root of theta. So we can make that positive quantity. Eventually, it goes down with the square of theta. The other one only goes down with linearly in theta. So eventually, it's possible to make the red guy negative and smaller than the absolute value than the yellow guy. Unless it's the case that we absolutely have this, which is, as you can see, the same condition here. That's equation 18.45. Okay. So conversely, if we've got 18.45 and we construct any convex combination of the vertices, then when we take Y times X star, that's going to be equal to its form in terms of the convex mixture. But then each of the Pi transpose, each of these guys are going to satisfy this condition, and so each one individually is something that gives us this inequality, which then gives us this because it's a convex combination. The sum of the lambda i's is equal to 1. So that therefore implies that Z is greater than or equal to that. And I guess there's a little bit of a typo here. Let me just fix the typo. Does anyone see the typo? This should really be Z here in each of these cases. Okay. Okay, theorem 1. Theorem 2. The set Q in the minimum normal algorithm is always affinely independent. Why is that? When we add one point, it's always affinely independent, right? Clearly. So after line 2, again, looking at your sheet here, we're trying to prove something about the algorithm. So after line 2, it's clearly affinely independent. So you can see that the only thing we can do with deleting points. So there's a little bit of a typo here as well. Sorry, but in line 7, we add a single point, and in line 15 we can delete some points. Right. So either we delete one or more points from Q, or we add one point. Any form of deletion doesn't destroy the affine independence. If you've got an affine independent set of points, any subset of the affinely independent set of points is affinely independent. Remember, in fact, we know that from the perspective of, we defined geometries, combinatorial geometries of matroids using affinely independent sets in a space. So it's subclusive. Affinely independent points are subclusive. So the only worry we have is in line 7 that potentially might destroy the affine independence. Now, before we do line 7, we know that X star is the minimum norm point in affine hull of Q. And we get that from line 11, because basically we get to line 7 by first breaking out of the minor loop in line 12. right? And in line 12, we have x star is both in the affine hull of Q and then the convex hull of Q, right? So whenever we're in the affine hull of Q, we have that the affine hull is a subset of the hyperplane in x star, right? So x star is normal to the affine hull. So I guess the picture, if you want a geometric picture, is sort of like, here's x star, and here's the affine hull of Q. And the affine hull of Q then is going to be some subset of the hyperplane, which is sort of everything. Because the hyperplane is always, by the fact that it's a hyperplane, it's always going to be n-1 dimensional subspace, right? So then when we choose in line 6, like what is line 6 doing? It's choosing a point closer to 0. So we're choosing a point outside of h of x star. And so that basically means we're choosing a point outside of the affine hull. So therefore, we must retain affine hull. We've kept independence since we're not choosing a point in the span, in the affine span of Q. And so when we choose x hat and we add it to Q, we still have an affine independent set. So the updated Q in line 7 is affinely independent as long as Q itself is affinely independent. So we've maintained this invariance. Okay? So this is really important because basically the affine independence gives us a lot of things. It gives us the linear solvability. It gives us the fact that when we construct x in the affine hull of Q, and we have x as a weighted combination of points in Q, that there's a unique set of weights, right? Because the point is that if you had a set of Q that wasn't affinely independent, there would be more than one way of taking combinations of points in Q to give a particular point, to get an affine combination of points. But thanks to the affine independence of Q, we're guaranteed that when we represent x as a affine combination of points in Q as a weighted sum where the weights are W, it's unique. The other benefit is essentially it gives us a really easy way of solving this problem. This is the problem in line 9, which I said was potentially a worry. So when Q is affinely independent, this is relatively easy. And basically, we just do this solver. We just do this linear solver. And I think this is one of the most straightforward parts of the Wolf paper, so I'm not going to spend any detail on this. But basically, like I said, it's just a linear solver. And moreover, once we've done it, we essentially get this coefficient. We get what we solve for is W, the affine coefficients. Right? The affine coefficients are what we get as a result of the linear solver, which both gives us x by doing Q times W. And moreover, we can check this line where it is, line 10. We can check line 10 just by checking that W is non-negative. Then it becomes in the convex hull. So that's really simple. Now I also want to address lines 14 and 15 here. So basically, we're always doing this thing where we're sort of representing like x star as a convex or affine coefficients, and x naught as well with v. So basically, we've got W and V. And W is the coefficients for x star, and V are the coefficients for x naught. W and V is the same notation that Wolf uses in his paper. So if you go to that section, step 3 on page 133, you'll see W and V. This is the W and V that we're talking about. And that actually allows us very, very simply in linear time to solve lines 14 and 15. So we're doing pretty good, right? The only thing we haven't yet done is to see how we can solve lines 4 and 6. And I want to try to do this in the next 10 minutes. And now we're going to do this in the context of this theorem. The theorem says that the minimum norm algorithm finds the minimum norm point in convex hull of P after a finite number of iterations of the major loop. We know that the minor loop costs n cubed. We don't know how many iterations of the major loop happen, but we know that it's got to be finite, assuming numerical issues are addressed. And one of the issues that the Wolf paper actually has a number of details about how to deal with the numerics, because when you're dealing with finite precision floating point numbers, you have to deal with the numerics. Otherwise, you might actually not, in practice, get termination. So you have to define thresholds and tolerances and things like that. And then there are also, by the way, I should mention there are a number of tricks in the Wolf paper to speed up the algorithm. You're welcome to implement them if you want. If you truly want to win this contest, you probably should. However, it's not necessary. I mean, if you just get it working. I mean, the functions we're going to give you, I mean, you should ask Rishabh. He's got all the details of which functions he's going to give you. And also, by the way, I should mention that you should ask if you have any questions about the actual C++ code and the stubs and everything, Rishabh is the guy to talk to. He's the master of that. But I guess one of the things that you will need to do is deal with some of these tolerances, just because you might run into numerical issues otherwise. And I would suggest doing everything in double precision. Just it'll make things a little bit nicer. But anyway, let's go back to this proof for a minute. So in the minor loop, starting at line 8, so like I said, one invariant we have is that we have x star always stays within the convex hull of Q. We saw that before, right? So in line 16 as well, so even when we delete, we argued that before, that in line 15 we make sure that the assignment in line 16 that happens ensures that x star is still in the convex hull of the new Q, the Q that results after line 15. Okay? So every time x star is updated in the minor loop, its norm never increases. In the example that I saw, that we gave you, the geometric example, we saw that the norm was strictly decreasing at points inside of the minor loop. In general, what we have is that the norm never increases. I mean, and so like before line 8, we have, before line 11, we have that x naught, that the norm of x naught is less than or equal to the norm of x star. And the reason why we have that is because x star is in the affine hull of Q, and x naught is in the minimum over the affine hull, right? So another way of looking at this is that the old x star is in the convex hull of Q. X naught is the minimum of the affine hull of this updated Q, and it also happens to also be in the convex hull, so therefore it must be truly the minimum norm point in the current Q. So therefore, we have this bit here. Okay? And let me just fix this again so this is not confusing. This is line 11 again. Similarly, before line 16, this is the correct line now, line 16, we have that the y, which we've computed in line 14, has norm no greater than the norm of the current x. Now the reason why we have that is, again, because of this invariant. So x star stays within the convex hull of Q. We have that x naught is in the affine hull of Q, but x naught is not in the convex hull of Q because we checked in condition on line 10 and that was false. Okay? So therefore, we've got that the 2 norm of x naught is going to be less than 2 norm of x star. Now, the question is, how many times does the minor loop run? So the number of iterations of the minor loop can't be any more than the dimensionality of the convex hull of Q. And since Q is specified by a finite number of points, the dimensionality can't be any bigger than size of Q minus 1. Right? So basically, and that's good. So basically it means that the minor loop terminates. So and here's why this happens. So each iteration of the minor loop removes at least 1 point from Q in line 15, right? So we're removing at least 1 point. Again, because x is not in the convex hull of Q, which basically must mean that there's some point of Q not on the face of the convex hull of Q where y lies. Right? That's just a necessary condition. So then eventually what happens is that Q is going to reduce to a singleton, right? And the minor loop is always going to terminate when Q is a singleton. Right? Why is that the case? Because clearly lines 9, 10, and 11 are going to be executing in that case. So the minor loop then terminates in a finite number of iterations, of the number of iterations at most dimension q. And in fact, what's interesting is that the total number of iterations of the minor loop in the entire algorithm, just if you just had a counter and every time you got into the minor loop you bumped up that counter, that would be no more than the number of points in P. Because what's happening is like we are adding, in line 7, we're adding points to Q that we're never adding points that have been previously removed because the norm is going to be decreasing. Because the way that we're creating these hyperplanes. So that means that if there's an exponential number, now this might not sound good for the base polytope because there's going to be an exponential number of points in the base. Right? But it's finite, at least. All we're proving here is finiteness. And this is one of the questions, because when you have a submodular polytope, it's not clear how many times this is going to run guaranteed. Okay. Here's now what's something that's very, very critical. So each major loop in line 11 when the minor loop, so basically what's going to happen is the minor loop, there's going to be points when the minor loop returns in one iteration. So each time that happens, the norm of x star is going to be strictly decreasing from what it was before. And to see this, basically we look at the following. So let's say we take x hat, that's defined at line 7, and x star, which is defined at line 11. And we look at the convex combination of both. They both live within the convex hull of Q. And so we have this being true. And this is sort of the same kind of trick. We then look at this convex combination, we complete this square, and this implies that this is true. Okay? This is greater than x naught, and the reason why is because x naught is equal is the min of the affine hull. Okay? So x hat is going to be, because it's chosen to be on the same side of the origin of x star, of h of x star, the hyperplane at x star, we have this inequality. And so when that inequality happens, then we've got this being true strictly. Okay? And so that basically means that we've got an algorithm which has, where the inner loop occurs in a finite number of iterations. The minor loop occurs with a finite number of iterations. The major loop is such that we're strictly decreasing the norm at each iteration, and there's a lower bound. So if we're strictly decreasing the norm at each iteration, there's a lower bound, it will eventually terminate. But maybe in exponential time. Now, the question is, for how small, for this to occur, we need to have theta to be small. So, like, all of this stuff was contingent, very similar to what we saw before, on theta being small. Because again, this issue where theta being small is such that this is true, because otherwise the opposite is going to happen, where this second term here might dominate, since that guy's always positive. And so the way we do that is by solving for theta. And so theta, for any theta less than this quantity, which solves for theta, is going to be such that the norm of x star is going to be strictly greater than the norm of x naught. And that's going to be the thing that gives us the strict decrease at each major iteration. And this is actually, you might already start seeing Edmonds' greedy algorithm in equation 18.15. You'll see in a second. So basically, we can also show, for the same reason that we have x, the norm of x star strictly decreases each time q is updated in line 7, followed by updating in line 16. Same basic argument holds. And so therefore, in each iteration of the major loop, the 2 norm of x star decreases. And so the minimum algorithm terminates and it does so. So now, a couple of other things I want to say. The near side means that the side that contains the origin. Now when we do this in line 6, we want to find the x star that reduces the min norm is as much as possible, or the norm point as much as possible. Right? Now that potentially might be hard. Now here's the actual reduction. So delta is the reduction here, which is this. And then from the expansion, looking at the difference, sort of the convex combination of x star and x naught, that reduction is lower bounded by this quantity, which is a function of theta. And let's just define that delta sub bar. Okay, so that's a lower bound on the reduction, and we want to maximize delta sub bar, okay, to have the greatest reduction possible. And then whenever theta, like we said in the last slide, is between this value, we can maximize over theta of delta sub bar, and we get this quantity here. So this is a quantity which is the best possible theta we can get. And it's a function only of x star, which we've got, and x hat, which is the thing we want to choose. So basically now this leads us to a choice of a guaranteed choice of x hat, that if we choose it, we're going to get this reduction, the strict reduction. Now where does x hat live? X hat lives in the denominator and the numerator. And so we might then say, okay, well, we just choose x hat that's inside of the polytope that maximizes this quantity to get the greatest reduction. That'll give us the largest norm reduction. But there's a problem, which is that this problem is just as hard as the minimum norm point problem to begin with. So we can't do this efficiently. So this is bad. I can put a little unhappy face here. But the happy part of this is that we can maximize the numerator, okay, without dividing by the denominator. We maximize the numerator of equation 18.53, and we choose this x. But then part of it is just a constant, and so now what we've got is this optimization problem for choosing x hat. Does anyone recognize that? That's solved by Edmonds' greedy algorithm. Except it's the min form, right? It's like finding the point within the polytope, which is really the base. Remember, this is every time we see p, we really mean b of f here, right? So it's finding the point in the base polytope that minimizes the dot product. The argument here is x star. So what we're going to do is, by solving this, equation 18.54, we're going to find the x hat that is, in some sense, is the largest distance to the hyperplane. Okay, and Edmonds is then, so what the Wolf paper talks about is an attempt to try to do this. What Edmonds' greedy algorithm does is it gets us this for the submodular base. So Edmonds does exactly what, and this is again what Fujishiki realized, which is really cool. So now we've, so this solution can be used to determine if the hyperplane separates it from the origin, which is in line 4, right here. And then if the point in P having the greatest distance to H star, which is again what Edmonds' greedy algorithm gives us, is not on the side where the origin lies, then H of P separates the convex hull from the origin. And so then in such case, we can check this. We terminate when we get the x hat from Edmonds' greedy algorithm, and we terminate the algorithm if this is true. Okay. And that's the thing that gives us equation 4, or sorry, line 4. Now in Wolf's paper, again, there's numerical tolerances you have to deal with. And what Wolf suggests is to use equation, not exactly equation this guy here, because that may be numerically unstable, but we have some epsilon tolerance parameter. And if epsilon is big, you're gonna stop earlier, but you might get the wrong answer. If epsilon, and a lot of the empirical work is, for example, like trying to find good epsilon. Fujishiki talks about, for example, when you have integral polymatroid functions, then you can set epsilon very easily. But in general, for any arbitrary polymatroid function, it's not, you need to define epsilon in some way. All right, so I've already said this. Equation 18.54 can be solved using Edmonds-Greedy algorithm. And so, again, Edmonds' discovery is one of the main reasons why the min-norm algorithm gives us a reasonable algorithm. So there's, I want to sort of put this in the context of submodular function minimization. So this is a slide that's modified from Iwata. Iwata had this slide that talked about submodular function minimization. And his slides, I hope he doesn't mind that I did this, but basically his slide included this stuff down here. And what I've added is Edmonds, because I think Edmonds is really the root of all of it. Because Edmonds enabled this whole string of papers. Edmonds also enabled the ellipsoidal method, which we defined. And then there's the Wolf procedure, which was also, there's a similar procedure by von Hohenbalken, which led to Fujishige using Edmonds to give us the minimum norm point algorithm. And then very recently, there's been, if you look at the 2013 version of Francis Bach's book, he uses a large assortment of different primal convex optimization procedures, including the Frank-Wolf procedure, which is different from the Wolf procedure, but a number of other polyhedral convex optimization problems to minimize the submodular function, and benchmarks them all. And finds that the min norm is basically as good as any of them, that none of them seem to do any better. And this is from speaking to him directly, is convinced that if you, like I said last time, if you spend enough time on any of these procedures, you can get them to work fastest, based on doing a good implementation. So there doesn't, in other words, there doesn't seem to be any mathematically clear winner based on the experiments that he did. But on the other hand, I mean, I think using the proximal methods give us a whole tool set of convex minimization methods for doing the submodular minimization. And then to this day, it's still the case that the min norm is state of the art. I'm not done. I know I'm running late, but this is important because I want to finish this slide, these slides for your project. The currently fastest strongly polynomial time algorithm has got complexity n to the fifth t times n to the sixth, where t is the time for doing one function evaluation. That's by Orlin. So that's obviously not practical, but it's a guarantee, upper bound. The lower bound for submodular function minimization is not known. I should mention that this whole slew of papers down here, which leads to this, all basically utilize a lot of the concepts like SAT and depth and some of these things that we've defined earlier. So all of that stuff and the lattices are all important for understanding those. Fujishige and Isotani's paper report minimum norm in practice, but they only use a very limited set of submodular functions, the Iwata functions. There are some obvious facts about the minimum about the minimum norm complexity. So each major iteration requires a linear number of function calls. The complexity of each major iteration is at least n cubed. So each time you run one major iteration, it's n cubed because you're doing this linear solver, which is the affine projection step. And so therefore, the complexity of each major iteration is n cubed plus n to the 1 plus p, where each submodular function evaluation itself requires, say, n to the p for some constant p. The real question is, how many major iterations are unknown? Or how many major iterations does it require? And maybe this is something you can try. You can report. When you're doing your code, you can count how many major iterations it requires. I do have some initial results. These are results that were generated by my student, Hui Lin. And they show for, let me just zoom in. This was surprising, something that we discovered where, here we go. So this is the class of functions down here. It's basically, let me just define this a little bit, just so. So n of s, this is too big, hold on. Here we go. N of s is the bipartite neighborhood function. And then W is weighted bipartite neighborhood, and this is a bipartite neighborhood for an application that we were working on in our lab for doing speech corpus subset selection. And this is a story, this is an anecdotal story, since I might as well end on something that's somewhat anecdotal. We were actually trying to solve this problem, this application that used submodular function minimization for selecting subsets of a speech corpus. And we were using the min norm algorithm. that my student implemented, Hui, and we were finding that it was running exceedingly slow, exceptionally, horribly slow. And we looked at the Fujishige and Isotani paper, and they said, oh, it's only n to the fourth overall, meaning that you only need n major iterations. But then the function that we wanted to minimize was this function. So we have a modular function, or negative of a modular function, plus some constant times a power, which is between 0 and 1. So it's basically a concave function over the bipartite neighborhood function. And we know from earlier theorems in this class that you can compose a non-decreasing concave function with a polymatroid function, you've got a polymatroid function. And then when you add a modular function, you've got a submodular function. Now this is a big problem. This is actually a very, very big graph with tens or hundreds of thousands of ground elements. Bigger than the class of functions that were considered in the Fujishige and Isotani paper. And what we found was that basically the difficulty of the min-norm algorithm depends very much on the constant alpha. So if you change alpha, and the alpha sort of controls a degree of the curvature of the function to some extent. So it says, well, how much do we want to have sort of global additional diminishing returns over the neighbors in the bipartite neighborhood function? So let's take a look at some of these guys. So here's something that's similar to, I'm sorry it's taking a long time to refresh, but here's something that's similar to the Fujishige and Isotani paper. So this on the horizontal axis is the log of the ground set size, right? So it's really the ground set size is like 2 to that guy. And the vertical axis is the log of the number of major iterations. And what we did is we sampled different subsets of this very, very large bipartite neighborhood graph so that we have different ground set sizes, and then run averages over multiple different subsamples of a particular size. And you could see that you have two curves, one which is based on the average, which is the red stars, and one which is based on, it's an interpolation based on the averages, and the black one is an interpolation based on the worst case. And in this particular case, when alpha is equal to 1, we essentially get something that seems to suggest that the number of major iterations is linear in n, which suggests min norm is n to the fourth. However, you get a very, very different picture for different values of alpha. All of a sudden, when we choose a different submodular function, where we have a different type of curvature, the min-norm algorithm seems to perform much, much worse. And in fact, if we interpolate either the average points or the worst case points, I think what I said last time was the opposite. So the red is the interpolation of the worst case points, and the black is the interpolation of the average points. And you can see that at each ground set size here, we have essentially a histogram of the running times of the min-norm algorithm. And you can see that the two lines correspond. Remember, this is the number of major iterations. And so, for example, like take the black line, which is the interpolation of the average points. That seems to suggest that if each major iteration is n cubed, that the min-norm algorithm runs as n to the 6, n to 6.3 or something, because we just add the powers. So this suggests that it's approaching the complexity of the combinatorial algorithms for certain submodular functions. And you can see, if you look at this slide, that there are some other ones as well. The worst case we could find was that one where it's about n to the 6.3 or something. But it seems to suggest that the min-norm algorithm is not n to the fourth, at least empirically. Now, we don't know. It's very, very hard to measure empirical asymptotic performance, since it could be looking like n to the 6 for a while, and then eventually it'll level off at n fourth. I mean, when n gets big enough. But like I said, this is suggestive that maybe it's going to be worse than n to the fourth. Now, maybe someday one of you will prove the true lower bound of the min-norm algorithm, and will be very famous. So, and maybe someday you'll humbly recall back the days of taking EE 596A. Is that what this course is called? I can't remember. But whatever this course is called, you'll come back and recall taking this class and be happy. Okay, so before you go, I apologize for running so late, but I thought this was very important. If you have any questions, please do start on your implementation now. Don't wait till the last minute. This is a very, very non-trivial project. I've given you what I hope is enough fuel and boot material to understand the algorithm. I will try to get this video on YouTube as soon as possible if you find these lectures useful for something. But please don't delay. And then also, if you have any questions, post to the forum. And we'll try to get them answers as soon as possible. Okay, thank you, and see you on Wednesday. Wednesday we're going to talk about submodular max, a totally different topic.